So today we're going to discuss some properties and limits that some of these you may have seen last year. Some may be new to us. So let's take a look first of all at some properties and limits. First of all, let's take a look first of all at this particular situation. The limit is x approaches c is equal to L, and the limit is x approaches c is equal to k. Again, c is just an x value. So the first property of limits we're going to talk about is your scalar multiple. When we talk about a scalar multiple, scalar is a very common word we're now going to use in calculus. We're going to move away from using that word constant. So a scalar is just a constant or a number. So basically the way the scalar multiple property of limits works is if you have a constant multiplied by some function, and we want to find the limit as x approaches c, what we can actually do is we can actually pull that constant out, find the limit as x approaches c of f of x, and then we can multiply that constant by the limit that we find. So we'll take that constant. So that's our constant rule. We also have a sum and difference. So in other words, if we're trying to find the limit of a sum, then it's equal to the sum of their limits. So I can find the limit of f of x, which is L. I can find the limit of g of x, which is k, and I can add or subtract them together. So that's my sum or difference rule. Very similar for product. The limit as x approaches c. If I want to find the limit of a product, I can find the limit as x approaches c of f of x, and if that is L, I can find the limit as x approaches g of x, which is k, and I can multiply those two limits together. Same thing with my quotient rule. If I'm trying to find the limit of a fraction, I can take the limit of the numerator, which is L, divided by the limit of the denominator, which is k. Then I also have the power property. If I'm trying to find the limit as x approaches c of some function raised to a power, that power could be a whole number. That power could be a fractional exponent. So this also would, again, apply if you're dealing with a radical. Again, I could find the limit and then raise it to that particular power. Again, I want to say that the limit properties do not exist if the limit is x approaches c of f of x and the limit is x approaches c g of x fail to exist. In other words, you cannot add, subtract, or divide a number with a D&E result. So let's take a look at example 1. So we have the two functions. Again, we've got two graphs. I have f of x and I have g of x. So just pay attention to the graphs that are given. Now the limit as x approaches c. Now what you have to be careful of, again, when you look at the limit as x approaches 3 of f of x times g of x, what this question's asking me to do is to find the limit as x approaches 3 of f of x times the limit as x approaches 3 of g of x. Now, I know if I look at this limit as x approaches 3 for f of x, by itself, it's a D&E. However, because this is a two-sided limit, because I'm looking at the limit as x approaches 3, you have to go back to the definition of a two-sided limit. In other words, the limit as x approaches 3 of the left of f of x times the limit as x approaches 3 from the left of g of x has to be equal to the limit as x approaches 3 from the right of f of x times the limit as x approaches 3 from the right of g of x. So just because when you look right here, it appears that this limit does not exist, remember, you're taking the limit of a product. So in other words, you have to go back to the definition of a two-sided. Before you say this is a D&E, you've got to look at the limit of the products from the left to see if they're equal to the limits of the product from the right. So when I look at the limit as x approaches 3 from the left, so when I look at the limit as x approaches 3 from the left, I see that it's approaching a y value of 1 times the limit as x approaches 3 from the left of g of x. So as I'm approaching 3 from the left of g of x, it's approaching 0. I need to check see if it's equal to the product of the limits from the right. So limit as x approaches 3 from the right of f of x. So as I'm approaching 3 from the right, that's going to be 3. The limit as x approaches 3 from the right of g of x is 0. So then I do have a 0 equals 0. So then what I know is that the limit as x approaches 3 of f of x times g of x is equal to 0. So you can't just look at this a rigid problem. Just because this is a DNE, you have to double check the limits from the left to be equal to the limit from the right. So let's take a look at the next examples. The limit as x approaches 3 of f of x plus f of x plus 3. So when I look at the limit as x approaches 3 of f of x plus the limit as x approaches 3 of f of x plus 3. Now, when you see this composition in terms of x plus 3, what this is going to do is I have to plug 3 into this particular function for x, and I'm going to create a new x value for this particular limit. So I have the limit as x approaches 3 of f of x, so that first part hasn't changed, plus, when I add 3 plus 3, that gives me a 6. So I have the limit as x approaches 6 of f of x. So again, if I look here, as we discussed in the previous problem, the limit as x approaches 3 is a DNE. So we have to go back to the definition of a two-sided limit. So I have to look and see here, I'm going to look at the limit as x approaches 3 from the left of f of x, plus the limit as x approaches 6 from the left of f of x. And I have to check to see if it's equal to the limit as x approaches 3 from the right of f of x, plus the limit as x approaches 6 from the right of f of x. So again, when I look at my graph for f of x, the limit as x approaches 3 from the left of f of x, as I can see, is 1, plus the limit as x approaches 6 from the left for f of x. So as I approach 6 from the left of f of x, that's going to give me a 2. I have to check to see if it's equal to the limit as x approaches 3 from the right of f of x. So as I approach 3 from the right of f of x, again, that's going to give me a 3. The limit as x approaches 6 from the right is going to give me a 0. So I know that 3 is equal to 3. So since the left-hand side of the sum of the limits is equal to the right-hand side of the sum of the limits, then I know that the limit of this particular problem is going to be equal to 3. So you have to check the sum of the limits from the left and the right. So let's take a look at C, which is my product rule. So again, I have the limit as x approaches 6 of f of x times the limit as x approaches 6 of f of x minus 1. Well, first of all, like I did in the previous problem, I know when I plug in my x here, that's going to change the limit that x is approaching. So I have the limit as x approaches 6 of f of x times the limit as x approaches, and again, 6 minus 1 is 5, of f of x. So again, if you take a look at the graph of f of x, I know the limit as x approaches 6 by itself is a DNE. So I need to look at my limits from the left and compare them with the limits of the right of this product. So I have the limit as x approaches 6 from the left of f of x times the limit as x approaches 5 from the left of f of x. Check to see if it's equal to the limit as x approaches 6 from the right of f of x times the limit as x approaches 5 from the right of f of x. So as long as they're both equal to one another, as both of these products are equal, then I can find the limit. So the limit is x approaches 6 from the left. So as I'm approaching 6 from the left, that's giving me a 2 times the limit as x approaches 5 from the left is going to be 0. I'm checking to see if it's equal to the limit as x approaches 6 from the right. So the limit as x is approaching 6 from the right is 0. The limit as x approaches 5 from the right is 2. So 0 equals 0. So this particular limit is going to be equal to 0. So again, when I look at here, I have to find the limit of this sum. So the limit is x approaches 3 of f of x. Plus, again, remember, I'm going to plug that 3 in for x. The limit as x approaches, again, 3 plus 1 is 4 of g of x. Again, we've already discussed this. This limit as x approaches 3 of f of x, we know is a D&E. So I have to check my sum of the two-sided limits. So the limit as x approaches 3 from the left of f of x plus the limit as x approaches 4 of g of x from the left is equal to the limit as x approaches 3 from the right of f of x plus the limit as x approaches 4 from the right of g of x. So when I find this limit from the limit as x approaches 3 from the left, as I've done, that's going to be 1 plus the limit as x approaches 4 from the left. So as I approach 4 from the left, that's going to give me a 1. Check to see if it's equal to the limit as x approaches 3 from the right. Says as I approach 3 from the right, that's a 3. The limit as x approaches 4 from the right is 0. So I have 1 plus 1, which is 2, which does not equal 3. So I know this is going to be a D&E. So this is a separate handout of the notes. This part was actually inadvertently left out of the note packet. So I did hand this out in class. So it is available in Schoology, or you can come see me and get an extra, or just take notes on a separate sheet of paper. So now we're going to talk about a property of limits when you're dealing with composition. Remember, when we talk about composition of functions, just a kind of a quick review. Remember when you back in Algebra 2 or Pre-Calc, a composition of functions when you have f of g of x. You have your inner function, and then you have an outer function. So when you take a look at trying to find the limit of a composition of functions, the main concept here is you're looking at, actually, we always start with the inner function. So we're going to have to start by taking the outer function of f, and I'm going to start by finding the limit as x approaches a of that particular inner function. So the limit is x approaches a of g of x. Now, what has to happen is after you find the limit, you have to ask yourself, is f continuous at the limit of the inner function? So as long as the limit as x approaches a of g of x, whatever value we get, as long as f is continuous, then I know I'm just going to be taking the value of f at that particular limit. So in words, the limit of f of g of x as x approaches a is the limit as x approaches a of g of x. So we have not studied the true definition of continuity just yet. We are leading up to that. So I am going to skip a couple of these problems just to help us out here. So I'm going to skip number 1. Let's take a look at example number 2. The limit as x approaches 1 of g of f of x. So in other words, what this problem is asking me to do is I'm going to find g of the limit as x approaches 1 of f of x. So the first thing I want to do is I want to find the limit of this inner function. So remember, f is the graph of f of x. So when I look at this particular graph, the limit as x approaches 1 is going to be -2. So then I'm looking at g of -2. The question you have to ask yourself, is g continuous at x equals -2? So again, remember this -2 is the limit. So again, now I have to look at g, which is my piecewise function. And again, remember, -2 is my x value. So which domain does -2 fit in? Is -2 greater than 1? Is -2 equal to 1? Well, I know that -2 is less than 1. So the question is, at x equals -2, is this function continuous? Well, 2x minus 1/3, that's a line. It's a line with a slope of 2, y-intercept of -1/3. I know lines are continuous for all real numbers. So the answer to this question is yes, it is continuous because I know it's a line. So then what I simply need to do is I need to find g of -2, which means I'm simply going to take -2 and plug it into this function for x. I'm looking at the defined value. So 2 times -2 minus 1/3, -4 minus 1/3 is equal to -4 and 1/3. So you have to look at that inner function and ask yourself the question. When you find that limit, you have to look at the outer function and ask yourself, is it continuous at that particular function? Let's take a look at number 3, f of x. So I need to figure out f of the limit as x approaches 1 of f of x. So I'm going to start by finding the limit of that inner function. So when I look at the graph of f, the limit of x as x approaches 1 is -2. So I have f of -2. So the question I have to ask myself, is f continuous at x equals -2? So when you look at the graph, we can see that at -2, there's no holes, there's no gaps, there's no intercepts. So the answer to this question is yes. So when you look at the graph now, I need to figure out what f of -2 is, which means I'm finding the point on that line. So at x equals -2, you can see you have a point on the graph, which is about -3 and -3 1/4, -3 1/2. You do have to estimate that. So we'll just say it's about -3 1/2. So that's how we do composition. Again, if it's continuous, then again, you're looking at the outer function where it's defined. Now let's go back and see what happens when it's not continuous. So as I just mentioned, we just went over this particular notation. Again, when you have this limit notation, you're going to find the limit of the inner function and then evaluate the outer function. When we think of continuity, we're going to discover more about continuity later on this unit. That means that there's no hole breaks or asymptotes at x equals k. The problem we run into becomes very problematic if the inner function's limit does not exist or the outer function is not continuous at the value of the inner function's limit. So let's take a look at example 2a. The limit is x approaches 1 of f of x. So I know that I'm going to have to rewrite this as f of the limit as x approaches 1 of f of x. So again, I'm given two graphs. I'm given the graph of f of x. I'm given the graph of g of x. So just make sure we're reading the correct graph. So the first thing I'm going to do is find the limit as x approaches 1 of the inner function. So the limit as x approaches 1 of my inner function is 3. So now in order to answer this question, I have to ask myself, is f continuous at x equals 3? So when you look at the limit as x approaches 3, if f is continuous at x equals 3, you can clearly see it's not. The graph is disconnected. So the answer to this question is no. So before I go on my further explanation, let me just go over a review of composition of functions that you studied back in Algebra 2. So for example, when you looked at composition back in Algebra 2, let's think about an idea for a minute. So we know back in Algebra 2, you guys studied problems like f of g of 2. So maybe they gave you an equation that f of x is equal to x minus 1, g of x is equal to 2x plus 1. So the first thing you would do is you would evaluate this limit for g of 2. You would find g of 2. Remember, 2 was an X value or your input value. So I know I would take 2 and plug it into function G for an X. So I know that that would give me 2 times 2, which is 4, plus 1 is 5. So when I find G of 2, and I write 2 times 2 plus 1, that gives me 5. 5 is actually your output. So we know that G of 2 is equal to 5. 5 is your output. That is your Y value. But now what you're doing is you're taking 5 and you're going to substitute 5 into that composition notation for G of 2. So now 5 becomes your X value going into function F. So since 5 was an output on G, 5 is now your input for F. So I would plug 5 into function F, and that would give me a 4. So what happens is that input of 2, when you evaluate it, that 5 becomes the output for G, but then 5 becomes the input for F. So now let's go back to this particular problem here. So if you take a look at this particular function, if we discover that the function F is not continuous at 3, you have to look at the way we discovered the limit back in this first step. So if you look at the way we found the limit as x approaches 1 of f of x, notice the limit as x approaches 1 from the left and from the right. Remember, we find limits, we're looking at those x values slightly smaller. Notice as I approached 1 from the left and from the right, all of those y values were slightly smaller. And when we think about limits, when we say slightly smaller, we're thinking from the left. Now, these are your y values. But remember, when you're doing composition notation, what happens is when those output values become the input. So because this function is not continuous at 3, and because all of these y values, when I discovered this limit as x approaches 1, what I'm going to now have to do is to find the limit as x approaches 3 from the left of f of x. I'm looking at those x values that are slightly smaller than 3. Because remember, these output values were slightly smaller than 3. So the limit as x approaches 3 from the left is going to be 1. So if you take a look at this next example, the limit as x approaches 3 of f of g of x. So I'm going to find f of the limit as x approaches 3 of g of x. So looking on the graph of g, the limit as x approaches 3 of g of x is 0. So the question I have to ask myself, is f continuous at x equals 0? So if you look at your graph, I'm going to erase some of this so we can kind of read it a little bit better. So the limit as x approaches, is f continuous at 0? You can clearly see that it's not, because you can see the limit from the left is not equal to the limit from the right, because here's my limit from the left. Here's my limit from the right. So now, if you go back to this limit that I found in the limit as x approaches 3, well, as I approach 3 from the left, notice the y values were slightly smaller than 3. The y values here were slightly larger than 3. So notice you have a limit coming from below the graph and above the graph. So because that's happening, this is going to be a D&E. So now let's take a look at the limit as x approaches 7 of g of f of x. So I have g of the limit as x approaches 7 of f of x. So again, I'm going to start with that inner function. The limit as x approaches 7 of f of x. So notice the limit as x approaches 7 of f of x. Notice you have a vertical asymptote at x equals 7. So I know that limit is infinity. So this is a statement that really doesn't make any sense. The question you're asking yourself, is g continuous at x equals 7? I mean infinity, excuse me. Infinity is not a number, it's a behavior. So it's not approaching a fixed number. So right away, this is going to be a D&E.